CIET NCERT presents audiobook Ganit Prakash, textbook of mathematics for grade 8.
Page number 48. Chapter number 3. A story of numbers. On the right side of the page, we are provided with a QR code, scanning which we can reach out to the additional resources to this chapter. 3.1 Rima's Curiosity. One lazy afternoon, Rima was flipping through an old book when, whoosh, a piece of paper slipped out and floated to the floor. She picked it up and stared at the strange symbols all over it. What is this? She wondered. She ran to her father, holding the paper as if it were a secret treasure. She looked at it and smiled. Around 4,000 years ago, there flourished a civilization in a region called Mesopotamia, in the western part of Asia, containing a major part of the present-day Iraq and a few other neighboring countries. This is one of the ways they wrote their numbers. Here, we are provided with a picture of these numbers, which are written in the form of T. One T represents 1, and in the second column we have 2 T's, in the third we have 3 T's, in the fourth one there are 4 T's seen, and in the fifth one there are 5 T, and in the sixth one there are 6, and in the next 7, 8 and 9 respectively. Rima's eyes lit up. Seriously? These strange symbols were numbers? Her curiosity was sparked. Questions started swirling in her head. Here, we are provided with a picture in which Rima is holding a paper in her hand and father is sitting with a cup of tea in his hand. And some questions which are there in her mind are, since when have humans been counting? Since when have people been writing numbers in the modern form? What was their need for counting? What were they counting? How would the Mesopotamians have written 20, 50, 100? Page number 49. Sensing her curiosity, her father started telling her how the idea of number and number representation evolved over the course of time, across geographies, to finally reach its modern efficient form. Get ready to travel back in time with them. Humans had the need to count even as early as the Stone Age. They were counting to determine the quantity of food they had, the number of animals in their livestock, details regarding trades of goods, the number of offerings given in rituals. They also wanted to keep track of the passing days, example, to know and predict when important events such as the new moon, full moon, or onset of a season would occur. However, when they said or wrote down such numbers, they didn't make use of the numbers that we use today. Here, we are provided with a picture of Rima's father. He is explaining her about the idea of numbers evolved. The structure of the modern oral and written numbers that we use today had its origin thousands of years ago in India. Ancient Indian texts such as the Yajurveda Samahita mentioned names of numbers based on powers of 10, almost as we say them orally today. For example, they listed names for the numbers 1, Eka, 10, Dasha, 100, Shata, 1000, Sahasra, 10,000 Ayuta, etc. 1000, Sahasra, 10,000 Ayuta, etc. all the way up to 10 to the power 12 and beyond. The way we write our numbers today, using the digits 0 through 9, also originated and were developed in India around 2000 years ago. The first known instance of numbers being written using 10 digits, including the digit 0, which was then noted as a dot, occurs in the Bakshali manuscript, within brackets we have C. 3rd century CE. Aryabhatta, within brackets C. 499 CE, was the first mathematician to fully explain and do elaborate scientific computations with the Indian system of 10 symbols. On the right side of the page, we are provided with a picture in which 0 in the Bakshali manuscript is visible. The Indian number system was transmitted to the Arab world by around 800 CE. It was popularized in the Arab world by the great Persian mathematician Al-Khwarizmi, after whom the word algorithm is named, through his book on the calculation with Hindu numerals C825, and by the noted philosopher Al-Kindi through his work on the use of the Hindu numerals C830. From the Arab world, the Hindu numerals were transmitted to Europe and to parts of Africa by around 1100 CE. Though Al-Khwarizmi's work on calculation with Hindu numerals was translated into Latin, it was the Italian mathematician Fibonacci who around the year 1200 really made the case to Europe to adopt the Indian numerals. However, the Roman numerals were so ingrained in European thinking and writing at the time that the Indian numerals did not gain widespread use for several more centuries, but eventually, during the European Renaissance and by the 17th century, not adopting them became impossible, or it would impede scientific progress. Page number 50. Here we are provided with a quote of Perry Simon Laplace, 1749 to 1827. The ingenious method of expressing every possible number using a set of 10 symbols, each symbol having a place value and an absolute value, emerged in India. The idea seems so simple nowadays that its significance and profound importance is no longer appreciated. Its simplicity lies in the way it facilitated calculations and placed arithmetic foremost among useful inventions. Their use then spread to every continent and are now used in every corner of the world. Because European scholars learnt the Indian numerals from the Arab world, they call them Arabic numerals to reflect their European perspective. On the other hand, as noted here, Arab scholars such as Al-Khwarizmi and Al-Kindi called them Hindu numerals. During the period of European colonization, the European term Arabic numbers became widely used. However, in recent years, this mistake is being corrected in many textbooks and documents around the world, including in Europe. The most commonly used terminologies for the numbers we use today are Hindu numerals, Indian numerals, and the transitional Hindu-Arabic numerals. It is worth noting that the word Hindu here does not refer to a religion, but rather a geography / people from whom these numbers came. The shape of the digits 0, 1, 2, and so on up to 9 used to write numbers in the Indian number system today evolved over a period of time as given here. We are provided with a flow chart in which we can find the Brahmi script in which the numbers have been depicted. Then we can find the Hindu Gwalior in which the digits have been depicted. After that, we can find Sanskrit Devanagari. Here we find the way the numbers were written. We can also find the West Arabic, that is Gubar, and East Arabic in which the numerals have been depicted. Then comes 11th century Epses with different pattern of numerals being depicted here. Then we can find 15th century, the pattern in which numbers were written, and then 16th century Dura, the numbers were written in this pattern. Evaluation of the digits used in the Indian number system can be seen in this flow chart. Evaluation of the digits used in the Indian number system can be observed from this chart. Prior to the global adoption of the Indian system of numerals, different groups of people used different methods of representing numbers. Page number 51. We shall take a glimpse of some of them. We will not be looking at different systems in a chronological order, but rather an order that gives us the main stages in the development of the idea of number representation. But first, let us explore some of the foundational ideas needed to count and to determine the number of objects in a given collection. The mechanism of counting. Imagine that we are living in the Stone Age, say around 10,000 years ago. Suppose we have a herd of cows. Here are some natural questions that we might ask about our herd. Question number 1. How do we ensure that all cows have returned safely after grazing? Question number 2. Do we have fewer cows than our neighbors? Question number 3. If there are fewer, how many more cows would we need so that we have the same number of cows as our neighbor? We need to tackle these questions without the use of the number names or written numbers of the Hindu number system. How do we do it? Here are some possible methods. Method 1. We could tackle the questions by using pebbles, sticks, or any object that is available in abundance. Let us choose sticks. For every cow in the herd, we could keep a stick. The final collection of sticks tells us the number of cows, which can be used to check if any cows have gone missing. Here in the picture, there are 8 cows and there is one stick fixed in front of each cow. Page number 52. This way of associating each cow with a stick such that no two cows are associated or mapped to the same stick is called a one-to-one mapping. This mapping can then be used to come up with a way to represent numbers as given in the table. We have a tabular column here in which two columns are represented. One column has number and the other has its representation using sticks. Number 1, it has one stick against it. Number 2 has two sticks for its representation. For number 3, there are 3 sticks, and for 4, there are 4 sticks, and for 5, there are 5 sticks, and so on. How will you use such sticks to answer the other two questions? Question number 2 and question number 3. Method 2. Instead of objects, we could use a standard sequence of sounds or names. For example, we could use the sounds of the letters of any language. While counting, we could make a one-to-one mapping between the objects and the letters. That is, associate each object to be counted with a letter following the letter order. This mapping can then be used to come up with a way of verbally representing numbers. For example, we get the following number representation if we use English letters A to Z. Here, there is a table with 2 columns. One column has number and the other has its representation using sounds or names. In the first column, there is number 1 and letter A is written in front of it for its representation using sound or name. Similarly, number 2 has alphabet B against it. Number 3 has alphabet C. Number 4 has alphabet D. And number 5 has alphabet E. And so on. The number 26 has letter Z written against it. Page number 53. An obvious limitation of using only the letters of the English alphabet in this form is that it cannot be used to count collections having more than 26 objects. How many numbers can you represent in this way using the sounds of the letters of your language? Method 3. We could use a sequence of written symbols as follows. Here we are provided with a table in which we have 2 columns. One is for numbers and other is for representation using symbols. We have from numbers from 1 to 20 and their corresponding symbols are written in front of them. 1 is written as I, 2 with 2 I's, 3 with 3 I's, 4 with IV, 5 with V, 6 with V and I, 7 with V and 2 I's, 8 with V and 3 I's, 9 with I and X, 10 with X Roman numeral. Number 11 is written with X and I in front of it, 12 with X and 2 I's in front of it, 13 with X and 3 I's, 14 with X, I, V, 15 with X, V, 16 with X, V, I, 17 with X, V and 2 I's, 18 with X, V and 3 I's, 19 X, I, X and 20 with 2 X. Do you notice a way of extending this method to represent bigger numbers as well? How? From the discussion here, we notice that for counting and finding the size of a collection, we need a standard sequence of objects or names or written symbols. that has a fixed order. Let us call this standard sequence a number system. A collection of objects can be counted by making a one-to-one mapping between them and the standard sequence following the sequence order. Since there is no end to numbers, the challenge is to come up with an unending standard sequence number system that is easy to count with. Using sticks gives an unending standard sequence number system. However, it is not convenient to count larger collections as we will need as many sticks as the number of objects being counted. Using the sounds of the letters of a language, as in method 2, is convenient for the counting process but is not an unending standard sequence number system. The standard sequence number system given in method 3 was actually the system used in Europe before it got replaced by the Hindu number system. It is called the Roman number system. It was widely used in Europe for centuries and was convenient for many purposes but had the similar drawback that one cannot write arbitrarily large numbers without introducing more and more symbols. We will learn more about the system of writing numbers later on. Page number 54. Here, there is a picture of a boy sitting with pebbles all around him. As illustrated by the 3 methods, history gives us examples of number systems formed using physical objects such as sticks, pebbles, body parts, etc. Names and written symbols. Some groups of people had numbers represented both by physical objects as well as by names, while others, like the Chinese, had all 3 forms of representation. The symbols occurring in a written number system are called numerals. For example, 0, 1, 5, 36, 193, etc. are some of the numerals occurring in the Hindu number system. Numerals representing smaller numbers always had names, and so a number system composed of written symbols always went hand in hand with a number system composed of names, as in the case with the modern day Hindu system. Figure it out. Question number 1. Suppose you are using the number system that uses sticks to represent numbers as in method 1. Without using either the number names or the numerals of the Hindu number system, give a method for adding, subtracting, multiplying and dividing 2 numbers or 2 collection of sticks. Question number 2. One way of extending the number system in method 2 is by using strings with more than one letter. For example, we could use AA for 27. How can you extend this system to represent all the numbers? There are many ways of doing it. Question number 3. Try making your own number system. 3.2. Some early number systems. First, use of body parts. Many groups of people across the world have used their hands and body parts for counting. Here is how a group of people in Papua New Guinea used and still use their body parts as the standard sequence number system. Here there is a picture of a boy sitting with fruits all around him and has sticks in his hand for counting. Page number 55. Here we are provided with a picture of a boy with numbers marked on his upper body parts, beginning with his thumb as 1, fingers as 2, 3, 4, and 5, wrist as 6, forearm as 7, elbow as 8, then moving to his upper arm as 9, shoulder as 10, neck as 11, ear as 12, one eye as 13, nose as 14, other eye as 15, other ear as 16, likewise continuing on the other side and ending on his little finger with number 27. Second, tally marks on bones and other surfaces. One of the oldest methods of number representation is by making notches, marks cut on a surface such as a bone or a wall of a cave. These marks are also called tally marks. In this method, a mark is made for each object that is being counted. So, the final collection of marks represents the total number of objects. This method is very similar to the method of using sticks to count, that is method 1, except for the fact that a mark is made instead of adding a stick. Archaeologists have discovered bones dating back more than 20,000 years that seem to have tally marks. The oldest known such bones with markings that are thought to represent numbers are the Ishango bone and the Lebombo bone. The Ishambo bone, dating back 20,000 to 35,000 years, was discovered in the Democratic Republic of Congo. It features notches arranged in columns, possibly indicating calendrical systems. The Lebombo bone, discovered in South Africa, is an even older tally stick with 29 notches, estimated to be around 44,000 years old. It is considered one of the oldest mathematical artifacts and may have served as a tally stick or lunar calendar. On this page, at the bottom, we are provided with the pictures of Lebombo bone and Ishango bone. Page number 56. Third, number names obtained by counting in twos. A group of indigenous people in Australia called the Gumulgal had the following words for their numbers. Gumulgal, Australia. First one, Urapon. Second, Ukasar. Third, Ukasar, Urapon. Fourth, Ukasar, Ukasar. Fifth, Ukasar, Ukasar, Urapon. Sixth, Ukasar, Ukasar, Ukasar. Can you observe how their number names are formed? The number name for 3 is composed of number names of 2 and 1. The number name for 4 is composed of 2 occurrences of the number name for 2. Next question. Can you observe how the names of the other numbers are formed? The numbers are counted in twos, using which the number names are formed. 3 is equal to 2 plus 1. 4 is equal to 2 plus 2. 5 is equal to 2 plus 2 plus 1. 6 is equal to 2 plus 2 plus 2. Gumulgal called any number greater than 6 as Ras. There is a very interesting and puzzling historical phenomenon associated with this number system. Observe the following number system of a group of indigenous people in South America and the Bushmen of South Africa. Here we have picture of the world map representing different countries and the number systems they followed. Bakeri, 1. Tokali, 2. Ahagi, 3. Ahagi Tokali or Ahau, 4. Ahagi Tokali, 5. Ahagi Ohagi. Bushman, 1. XA, 2. T-OA, 3. QUO, 5. T-OA T-OA, 5. T-OA T-OA T-A, 6. T-OA T-OA T-OA. In Gumulgal, we have 1. Urapon, 2. Ukasar, 3. Ukasar Urapon, 4. Ukasar 5. Ukasar Urapon, 6. Ukasar Page number 57. Despite being so far apart geographically and with no trace of contact between them, these three groups have developed equivalent number systems. Historians have wondered how this happened. One theory is that these three groups of people may have had common ancestors who used this number system. In course of time, their descendants migrated to these places. Even though the number system of Gumulgal had number names for numbers only till 6, we can see the emergence of an idea here. Counting in twos is more efficient for representing numbers than, for example, a tally system. A general form which this idea has taken in different number systems is as follows. Count in groups of a certain number, like 2 in the case of Gumulgal system, and use the word or symbol associated with this group size to represent bigger numbers. Some of the commonly used group sizes in different number systems have been 2, 5, 10 and 20. You can find the idea of counting by fives in the Roman system, that is in table 1. This idea of counting in a certain group size and using it to represent numbers is an important idea in the history of the evolution of number systems. One of the phenomena that could have led people to this idea might be the human limit for immediately knowing the size of a collection at a glance. Let us try out the following activity. Quickly count the number of objects in each of the following boxes. Here we are provided with 9 boxes and various number of objects, and Rima is looking at them. In the first box we have 2 hens. In the next we have bunch of flowers with more than about 20 flowers. And in the third one there are 4 toys. In the fourth one we have about 10 ladders, 10 steps, and in the fifth one there is a dog. In the sixth one there seem to be group of grapes, maybe more than 40. In the seventh one we have about 5 tomatoes. In the eighth figure there are 9 pencils, and in the ninth figure there are 3 pyramids. Up to what group size could you immediately observe the number of objects without counting? Most humans find it difficult to count groups having 5 or more objects in a single glance. This limit of perception could have promoted people using tally marks to replace every group of, say, 5 marks with a new symbol. as observed in the system shown in Table 1. Page number 58. What could be the difficulties with using a number system that counts only in groups of a single particular size? How would you represent a number like 1345 in a system that counts only by fives? Even though counting in groups of a particular size and using it for a number representation is more efficient than the tally system, this method can still become cumbersome for larger numbers. The next system gives us a refinement of this idea. Fourth, the Roman numerals. Here we have a picture in which Rima and her father are standing near a Roman building and talking to a Roman. We have already observed that the Roman number system till 20 in Table 1, we have noticed that it uses I for 1, V for 5, X for 10. To get the Roman numeral for any number till 39, it is first grouped into as many tens as possible. The remaining is grouped into as many fives as possible, and finally the remaining is grouped into ones. Example, let us take the number 27. 27 is equal to 10 plus 10 plus 5 plus 1 plus 1. So, 27 in Roman numerals is XXVII. Instead of representing 50 as XXXXX, a new symbol is given to it, L. Following the way the number 4 is represented as 1 less than 5, that is, as IV, 40 is represented as 10 less than 50, that is, as XL. However, people using this system were not always consistent with this practice. Sometimes 40 was also represented as XXXX. The Roman number system introduces newer symbols to represent certain bigger numbers. Let us call all these numbers that have a new basic symbol as landmark numbers. Here are some of the landmark numbers of the Roman system and their associated numerals. Here we are provided with a box in which Roman numerals have been written and the numbers which they represent. For example, I for 1, V for 5, X for 10, L for 50, C for 100, D for 500 and M for 1000. Page number 59. These symbols are used to denote other numbers as well. For example, consider the number 2367. Writing it as a sum of landmark numbers starting from 1000 such that we take as many 1000s as possible, 500s as possible, and so on. We get 2367 is equal to 1000 plus 1000 plus 100 plus 100 plus 100 plus 50 plus 10 plus 5 plus 1 plus 1. So in Roman numerals, this number is MMCCCLXII. Figure it out. Question number 1. Represent the following numbers in the Roman system. First, 1222. Second, 2999. Third, 302. Fourth, 715. We observe that how vastly efficient the system is compared to some of the previous number systems that we have noticed. This system seems to have evolved out of the ancient Greek number system in around the 8th century BCE in Rome and evolved over time. It spread throughout Europe with the expansion of the Roman Empire. The efficiency of the system is due to the grouping of a given number by not just one group size, but a sequence of group sizes that we call landmark numbers, and then using these landmark numbers to represent the given number. This idea is the next important breakthrough in the history of the evolution of number systems. Despite the relative efficiency of the Roman system, it doesn't lend itself to an easy performance of arithmetic operations, particularly multiplication and division. Example, try adding the following numbers without converting them to Hindu numerals. A. CC XXXII plus CCCC XIII. Let us find the total number of i's, x and c's and group them starting from the largest landmark number. Apparently, it looks like the largest landmark number is C, but note that 5 C's, that is hundreds, make a D, that is 500. So the sum will be CC, CCC, 5 C's are combined to represent D, and we have 3x, 5 i's and cx, which can be represented as DC XL for 4x and II can be written as V. So, the number can be represented as DCXLV. Page number 60. Do it yourself now. B. L XXXVII plus L XXVIII. Next question. How will you multiply two numbers given in Roman numerals without converting them to Hindu numerals? Try to find the product of the following pairs of landmark numbers: V into L, L into D, V into D, VII into IX. Here there is a picture which reads Daredevil context, and the question put up is multiply CCXXXI and MDCCCLII. In this picture, we can find one of the contestants saying fight with a lion. People using the Roman system made use of a calculating tool called the abacus to perform their arithmetic operations. We will observe what it is in a later section. Here there is a picture which reads Daredevil contest, and the organizers have two different questions. First one says multiply CCXXXI and MDCCCLII, and the other one says fight with a lion. We can find many contestants standing for fighting with a lion and none with the multiplying of the Roman numbers. People using the Roman system made use of a calculating tool called the abacus to perform their arithmetic operations. We will observe what it is in a later section. However, only specially trained people use this tool for calculation. While going through the number system discussed above, it should not be misunderstood that historically one system developed as an improvement over the previous system. This point should be kept in mind when studying the upcoming number systems too. The actual story of how each of the number systems developed is much more complex and many times not clearly known, and so we will try not to trace this in the chapter. Figure it out. Question number 1. A group of indigenous people in a Pacific island use different sequences of number names to count different objects. Why do you think they do this? Question number 2. Consider the extension of the Gumulgal number system beyond 6 in the same way of counting by twos. Come up with ways of performing the different arithmetic operations like plus, minus, multiplication, division for numbers occurring in this system without using Hindu numerals. Use this to evaluate the following. Page number 61. First, Ukasar, 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 Urapon within brackets plus Ukasar, 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 Urapon within brackets. Second one, Ukasar, 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 Urapon within brackets minus Ukasar, Ukasar, Ukasar within brackets. Third one, Ukasar, 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 Urapon into Ukasar, Ukasar within brackets. Fourth one, Ukasar, 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 Ukasar within brackets divided by Ukasar, Ukasar within brackets. Question number 3. Identify the features of the Hindu number system that make it efficient when compared to the Roman number system. Fourth one, using the ideas discussed in this section, try refining the number system you might have made earlier. 3.3. The idea of a base. First one, the Egyptian number system. Here we have a picture depicting about the Egyptian number system. We can find some animals, a girl and a father standing with her. We are now going to observe a written number system that the Egyptians developed around 3000 BCE. In this system, we observe the use of landmark numbers to group and represent a given number. However, what makes this system special is its sequence of landmark numbers. Imagine making collections of pebbles. The first landmark number is 1. Group together 10 collections of the previous landmark number 1. Its size is the second landmark number, which is 10. Group together 10 collections of the previous landmark number 10. Its size is the third landmark number, which is 10 into 10, that is equal to 100, and so on. Here we are provided with a picture in which we have one bead which represents 1, and then collection of 10 beads representing 10, and next we have 10 beads arranged in 10 rows representing 100, and in the next one we have 100 sheets arranged one after the other in 10 rows, which represents 1000. Page number 62. Each landmark number is 10 times the previous one. Since 1 is the first landmark number, they are all powers of 10. The following are the symbols given to these numbers. 1 is represented with a line, 10 with an inverted U, 10 to the power 2 with a rope, 10 to the power 3 with a flower, 10 to the power 4 with a finger, 10 to the power 5 with a tadpole, 10 to the power 6 with a god, 10 to the power 7 with sun. As in the case of Roman numbers, a given number is counted in groups of the landmark numbers, starting from the largest landmark number less than the given number. This is then used to assign the numeral. For example, 324, which equals 100 plus 100 plus 100 plus 10 plus 10 plus 4 is written as 3 ropes, 2 inverted U's and 4 lines. Figure it out. Question number 1. Represent the following numbers in the Egyptian system. 10,458, 1,023, 2,660, 784, 1,111, 70,707. Question number 2. What numbers do these numerals stand for? First one, 2 ropes, 7 inverted U's and 6 lines. Second one, variations on the Egyptian system and the notion of base. Instead of grouping together 10 collections of size equal to the previous landmark number, as in the case of the Egyptian system, can we get a number system by grouping together 5 collections of size equal to the previous landmark number? Can this 5 be replaced by any positive integer? Let us examine this possibility. Let 1 be the first landmark number. Group together 5 collections of size equal to the previous landmark number 1. Its size is the second landmark number, which is 5. Group together 5 collections of size equal to the previous landmark number 5. Its size is the third landmark number, which is 5 into 5 is equal to 25. Group together 5 collections of size equal to the previous landmark number 5. Its size is the fourth landmark number, which is 5 into 25, that is equal to 125. Page number 63. Here we are provided with a picture in which we can observe one ball, and in the next we have group in which we have 5 balls, and in the next picture we have 5 groups of 5 balls in each group. Thus, we have a new number system where each landmark number is 5 times the previous one. Since 1 is the first landmark number, they are all powers of 5. 5 to the power 0 is equal to 1. For this, a symbol triangle is used. 5 to the power 1 is equal to 5. For this, 1 square is used for representation. 5 to the power 2 is equal to 25. In this, we have a hexagon which is used for its representation. 5 to the power 3 is equal to 125. Here, one circle is used to represent this. 5 to the power 4 is equal to 625. Here we have a curved line. 5 to the power 5 is equal to 3125. Here we have an upward arrow representing this number. Express the number 143 in this new system. Let us start grouping, starting with the size 5 to the power 3 is equal to 125, as this is the largest landmark number smaller than 143. We get 143 is equal to 125 plus 5 plus 5 plus 5 plus 1 plus 1 plus 1. So, the number 143 in the new system is 1 circle, 3 squares and 3 triangles. Number systems having landmark numbers in which the A, first landmark number is 1, and B, every next landmark number is obtained by multiplying the current landmark number by some fixed number n, is said to be a base n number system. The Egyptian number system is a base 10 system, and the number system that we created is a base 5 system. A base 10 number system is also called a decimal number system. Figure it out. Question number 1. Write the following numbers in the above base 5 system using the symbols in table 2. 15, 50, 137, 293, 651. Question number 2. Is there a number that cannot be represented in our base 5 system above? Why or why not? Question number 3. Compute the landmark numbers of a base 7 system. In general, what are the landmark numbers of a base n system? The landmark numbers of a base n number system are the powers of n starting from n to the power 0 is equal to 1, n, n squared, n cubed, etc. Page number 64. Advantages of a base n system. What is the advantage of having landmark numbers that are all the powers of a number? To understand this, let us perform some arithmetic operations using them. Example, add the following Egyptian numerals. We have 8 inverted U's and 7 lines plus 7 inverted U's and 8 lines. Let us find the total number of lines and inverted U's and group them starting from the largest possible landmark number. It has a total of 15 inverted U's and 15 lines. Since 10 inverted U's gives the next landmark number rope, the sum can be regrouped as sum is equal to 1 rope and 5 inverted U's and 16 lines. Page number 65. Since 10 lines gives a inverted U, we have sum is equal to rope and 5 inverted U's, 1 inverted U and 6 lines, that is equal to 1 rope, 6 inverted U's and 6 lines. Figure it out. First one, add the following Egyptian numerals. First one, 9 flowers, 6 ropes and 8 lines, and 5 ropes and 7 lines. Second one, 1 flower, 8 inverted U's and 5 inverted U's and 6 lines. 1 flower, 8 inverted U's and 4 inverted U's and 6 lines. Question number 2. Add the following numerals that are in the base 5 system that we created. Circle, 2 hexagons, 1 square, 2 triangles plus 3 circles, 1 hexagon, 2 squares, 2 triangles. Remember that in this system, 5 times a landmark number gives the next one. Page number 66. Rima says, I see a similarity in the method of adding numbers in the Egyptian and the Hindu system. A picture is provided here in which the calculations have been represented in Egyptian and Hindu system. Contrast the addition done in a base n number system with that done in the Roman system. In the Roman system, the grouping and the rearranging has to be done carefully, as it is not always by the same size that each landmark number has to be grouped to get the next one. The advantage of a number system with a base becomes more evident when we consider multiplication. How to multiply two numbers in Egyptian numerals? Let us first consider the product of two landmark numbers. Question number 1. What is any landmark number multiplied by an inverted U, that is 10? Find the following products. First one inverted U into another inverted U. Second one rope into one inverted U. Third one flower into one inverted U. Fourth one finger multiplied by one inverted U. Each landmark number is a power of 10, and so multiplying it with 10 increases the power by 1. Which is the next landmark number? Question number 2. What is any landmark number multiplied by a rope? Find the following products, where one rope represents 10 to the power 2. First one, inverted U multiplied by one rope. Second one rope multiplied by another rope. Third one flower multiplied by one rope. Fourth one, a finger multiplied by one rope. Page number 67. Find the following products. First one, inverted U multiplied by one tadpole. Second one rope multiplied by one flower. Third one flower multiplied by another flower. Fourth one finger multiplied by one god. Thus, the product of any two landmark numbers is another landmark number. Does the property hold true in the base 5 system that we created? Does this hold for any number system with a base? What can we conclude about the product of a number and inverted U, that is 10, in the Egyptian system? First one, 2 ropes multiplied by one inverted U is same as 2 ropes is equal to one rope plus another rope. So, 2 ropes multiplied by one inverted U is equal to, within brackets, one rope plus another rope multiplied by one inverted U. As these are numbers, the distributive law holds. So, one rope plus one rope within brackets multiplied by one inverted U is equal to one rope into one inverted U plus one rope into one inverted U. That is equal to one flower plus one more flower. That is equal to 2 flowers. Second one rope, 2 inverted U's, one line multiplied by one inverted U is same as one rope plus 2 inverted U's plus one rope. Thus, one rope, 2 inverted U's, one line multiplied by one inverted U is equal to, within brackets, one rope plus 2 inverted U's plus one line within brackets multiplied by 1 inverted u. Will the distributive property hold here? For the same reason that it holds for a plus b within brackets multiplied by n. It also holds when one of the numbers has more than two terms. For example, a plus b plus c within brackets multiplied by n is equal to an plus bn plus cn. So, 1 rope plus 2 inverted u's plus 1 line within brackets multiplied by 1 inverted u is equal to 1 rope into inverted u within brackets plus 2 inverted u's into 1 inverted u within brackets plus 1 line multiplied by 1 inverted u within brackets. That is equal to 1 flower plus 2 ropes plus 1 inverted u. That is equal to 1 flower, 2 ropes, 1 inverted u. Page number 68. Now find the following products. First one, 5 ropes, 2 inverted u's, 2 lines within brackets multiplied by 1 inverted u. Second one, 1 flower, 1 inverted u multiplied by 1 inverted u. What would be a simple rule to multiply a number with inverted u? As has been seen, a process of multiplying two numbers involves the multiplication of landmark numbers. When the landmark numbers are powers of a number, then their product is another landmark number. This fact simplifies the process of multiplication. However, this is not the case with the Roman numerals, which is why multiplication using them is difficult. Thus, a number system whose landmark numbers are powers of a number, that is, a number system with a base, is efficient not only in number representation but also in its utility in carrying out arithmetic operations. The idea of a number system with a base was a turning point in the history of the evolution of number systems. Our modern Hindu number system is built on this structure. Abacus that makes use of the decimal system. In around the 11th century, even the people still using the Roman numerals started using a calculating device, the abacus, constructed using a decimal system. It was a board with lines as given here in the figure. Starting from the line that stood for 1, each successive line stood for a successive power of 10. There is a picture provided here with Rima and father standing here and watching the abacus in front of them, which has different lines with 1, 10, 100 and 1000 with some beads in the abacus. Numbers were represented in it as follows. The given number was first grouped into the landmark numbers, that is powers of 10, in exactly the same way we have been grouping them so far. For each power of 10, as many counters were placed on its line as the number of times it occurred in the grouping. Page number 69. The presence of a counter above a line contributed a value of 5. For example, let us take the number 3426. It can be grouped as 3426 is equal to 1000 plus 1000 plus 1000 plus 100 plus 100 plus 100 plus 100 plus 100 plus 10 plus 10 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. This number was represented as given in the figure. Notice how the 6 ones are represented. To get an idea of how the abacus was used for calculations, let us consider a simple addition problem. 2907 plus 43. The two numbers were taken on either side of the vertical partition. Here, the picture of abacus is provided, which is depicting the addition problem 2907 plus 43, and Rima is trying to understand the same. How would you use this to find the sum? The counters along each line were brought together. What is to be done if the total in a line exceeded 10? Hint provided is, in this problem, the 7 ones and the 3 ones together make 10 ones, which contributes a counter to the line representing tens. Third, shortcomings of the Egyptian system. Despite being a number system that enabled relatively efficient number representations for numbers till a crore, that is 10 to the power 7, and relatively easy computations, the Egyptian system had a drawback. If larger and larger numbers needed to be represented, then there was a need for inventing an unending sequence of symbols for higher and higher powers of 10. Here, we notice the original challenge of number representation resurfacing in a different form. The next and the final idea in the history of the evolution of number systems not only solves this problem, but also remarkably simplifies number representation and computations. Figure it out. Question number 1. Can there be a number whose representation in Egyptian numerals has one of the symbols occurring 10 or more times? Why not? Page number 70. Question number 2. Create your own number system of base 4 and represent numbers from 1 to 16. Question number 3. Give a simple rule to multiply a given number by 5 in the base 5 system that we created. 3.4. Place value representation. First one, the Mesopotamian number system. Here, a picture of Mesopotamian civilization is given, and Rima and her father are watching the same. In the beginning, the number system used in ancient Mesopotamia had different symbols for different landmark numbers. In later times, it became a base 60 system, also called the sexagesimal system, with a very efficient number representation. It has puzzled many why they chose base 60. Different theories exist to explain this, ranging from the connection between 60 and the periods of some important events like the length of their lunar month, which had 30 days, or the time taken for the sun to complete one revolution around the earth when earth is taken to be stationary. The ease of representing fractions. We will not go into this here. Their earlier sequence of landmark numbers 1, 10, 60, 600, 3600, 36,000, etc., getting reduced to only the powers of 60 and so on. The influence of the Mesopotamian sexagesimal system, also known as the Babylonian number system, can be seen even now in our units of time measurements. 1 hour is equal to 60 minutes and 1 minute is equal to 60 seconds. This system used the symbols like T for 1 and less than for 10. Let us now briefly pause on the study of their number system and ideate on how one can build an efficient number system using the Mesopotamian features seen so far. Page number 71. Let us give our own symbols to their landmark numbers. 1 is represented with T, 60 is represented with a inverted square with number 1 inside, 60 square is equal to 3600 is represented with the help of an inverted square with number 2 inside, 60 cube is equal to 2,16,000 is represented with the help of an inverted square with number 3 inside, and so on. Note that we have actually used Indian numerals in creating these symbols. We could have invented our own symbols, but for the sake of easy recall and use, we have chosen to take help of the familiar numerals 1, 2, 3, etc. Using T and less than numbers from 1 to 59 can be represented. Here, there is representation of numbers from 1 to 59 using these symbols. There is also a picture provided for reproduction of a Mesopotamian tablet. Example: let us represent the number 640 in this system. Grouping it into landmark numbers, we see that 640 is equal to 10 into 60 plus 40. If we use the Egyptian idea, this number would be represented using 10 inverted square with 1 inside, and 40 would be represented using 4 less thans. Page number 72. Can we represent this more compactly? We can simply represent this number as 1 less than sign with inverted square and 1 inside and 4 less than signs, which can be read as 10 60s and 140, just as we have written in the equation. Example: let us try another number 7530. 7530 is equal to 2 multiplied by 3600 plus 5 into 60 plus 30. So, its representation would be a symbolic representation of 7530 is given here. Note that when a number is grouped into powers of 60, for its representation, no power of 60 can occur 60 or more times. If this happens, then 60 of them can be grouped to form the next power of 60. For example, consider the expression 1 into 3600 plus 70 into 60 plus 2 is equal to 1 into 60 square plus 60 plus 10 within brackets multiplied by 60 plus 2. That is equal to 1 into 60 square plus 60 square plus 10 into 60 plus 2. That is equal to 2 into 60 square plus 10 into 60 plus 2. Therefore, any number can be represented using the numerals from 1 to 59 along with the numerals from landmark numbers. Now, what if we make the representation even more compact by dropping the symbols for the different powers of 60 altogether? Here there is a pictorial representation of an earlier representation and our compact representation for numbers 640 and 7530. Page number 73. This is exactly what the Mesopotamians did. In their numeral, the rightmost set of symbols showed the number of ones. The set of symbols to its left represented the numbers of 60s. The next represented the numbers of 3600, and so on. Whenever there was no occurrence of a power of 60, a blank space was given in that position. It does not seem that the Mesopotamians arrived at this idea in the same way we did. Some scholars suggest that the similarity of symbols given to the landmark numbers 1 and 60 in their earlier number system and an accidental usage of them might have made them stumble upon this idea. Figure it out. First, represent the following numbers in the Mesopotamian system. First 163, second 132, third 200, fourth 60, fifth 3605. Thus, we can notice how the Mesopotamian system removes the need for the generating an unending sequence of symbols for the landmark numbers by making use of the positions where the symbols are written. Such a number system having a base that makes use of the position of each symbol in determining the landmark number that it is associated with is called a positional number system or a place value system. This idea of place value marks the highest point in the history of evolution of number systems and gives a very elegant solution to the problem of representing the unending sequence of numbers using only a finite number of different symbols. The Mesopotamian system, however, cannot be considered a fully developed place value system. It has certain defects that led to confusion while reading a number. Observe the representation of 60. What will be the representation for 3600? While writing the numerals, the spacing between symbols was not given the way we are giving it here. It was also difficult to maintain a consistent spacing for blanks across different manuscripts written by different people. These created ambiguities. For example, consider the representations of the following numbers. For the numbers 1, 60, 3600, 12, 602 and 36002, our representation and Mesopotamian representations have been provided in the table here. Page number 74. Because of the ambiguity in finding which symbols correspond to which powers of 60, the same numeral can be read in different ways. Even in our representation, which uses uniform spacing between symbols for different powers of 60, it is difficult to know the number of blanks between two sets of symbols, as in the representation of 3,60,002, as in the representation of 36,002. To address the issue arising out of blank spaces, the later Mesopotamians used a brilliant idea of assigning a placeholder symbol to denote a blank space. This is like the 0 we use in our system. Thus, 0, the symbol that shows nothingness, is indispensable as a placeholder in a place value system in which numbers are written in an unambiguous manner. Even with the problem arising out of blank spaces solved, other ambiguities still remained in the system. For example, the placeholder system was primarily used in the middle of numbers and not at the end. So they would not use it to represent a number like what we would write as 3600. Second, a Mayan number system. Here, there is a picture provided of Mayan civilization. Rima and her father are watching the same. In Central America, there flourished a civilization known as the Mayan civilization that made great intellectual and cultural progress between the 3rd and the 10th century CE. Among their intellectual achievements, stands their place value system designed independently of those in Asia. They also made use of a placeholder system for the modern day zero that looked like a seashell. Page number 75. The Mayan number system. On this page, we have a picture of Mayan number system in which almost a base 20 system has been explained. Landmark numbers mentioned are 1, 20, 20 into 18 is equal to 360, 20 square into 18 is equal to 7200, 20 cube into 18 is equal to 1,40,000. The symbols are also there on this page for 0 and dot for 1 and bar for 5. Symbols in the Mayan number system are placed vertically to represent a number. One numeral also has been explained on this page, and how they are read has been explained with landmark number positions, vertically placed symbols, and meaning of the symbols have been explained. Page number 76. Here we find a puzzling phenomenon. Why was their third landmark number 360 rather than 400? Some scholars feel that this might have something to do with their calendars. They used a dot for 1 and a bar for 5. These were used to denote numbers from 1 to 19. The symbols associated with different landmark numbers were written one below the other with the lowermost set of symbols corresponding to the number of ones, the set above corresponding to the number of 20s, the set above to the number of 360s, and so on. Question 1. Represent the following numbers using the Mayan system. First one, 77. Second, 100. Third, 361. Fourth, 721. Because the Mayan system is not an actual base 20 system, it lacks the advantages that a system with a base has for computations. Nevertheless, their place value notation and their use of a placeholder symbol for 0 is considered an important advance in the history of number systems. A curious fact is that we can still find the use of base 20 in the number names of some European languages. Third, the Chinese number system. Here, a picture of Chinese civilization has been given, and Rima and her father are watching the same. The Chinese used two number systems, a written system for recording quantities and a system making use of rods for performing computations. The numerals in the rod-based number system are called rod numerals. Here, we discuss the rod numerals, which are more efficient in writing and computing with numbers than the written system of the Chinese. The rod numerals developed in China by at least by 3rd century AD and were used till the 17th century. It was a decimal system, that is base 10. The symbols for 1 to 9 were as follows. Page number 77. On this page, Chinese number system has been depicted, base 10 or decimal. Numbers 1 to 9 have been represented here with the help of zongs and hengs. Zongs were vertical bars and hengs were horizontal bars. Note, the zongs represent units, hundreds, 10 of thousands, etc., and the hens, tens, thousands, hundreds of thousands, etc. A numeral with two horizontal bars, one horizontal and vertical bar, and 3 horizontal bars or 4 vertical bars. How is this to be read? we have 2 hengs as do horizontal bars, 6 zong, 1 horizontal and a vertical bar, 3 heng, 3 horizontal bars, 4 zong, 4 vertical bars. Landmark number positions were 10 to the power 1, 10 to the power 2, 10 and 1 respectively. That is equal to 2 into 10 to the power 3 plus 6 into 10 to the power 2 plus 3 into 10 plus 4 into 1. That is equal to 2634. Like the Mesopotamians, the rod numerals used a blank space to indicate the skipping of a place value. However, because of the slightly more uniform sizes of the symbols for 1 through 9, the blank spaces were easier to locate than in the Mesopotamian system. Page number 78. Notice how similar the rod numerals are to the Hindu system. The Chinese system with a symbol for 0 would be a fully developed place value system. Fourth, the Hindu number system. A picture of Indian number system has been depicted here with Rima and her father watching the same. Where does the Hindu/Indian number system figure in the evolution of ideas of number representation? What are its landmark numbers? And does it use a place value system? Here there is a picture provided in which Hindu number system has been depicted. Base 10 or decimal. 10 symbols 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A numeral 375. How is this to be read? Has been explained. Landmark number positions are 10 square for 3, 10 for 7 and 1 for 5. That is equal to 3 into 10 to the power 2 plus 7 into 10 plus 5 into 1. That is equal to 375. As can be noticed, the Hindu number system is a place value system. The Hindu number system has had a symbol for 0 at least as early as 200 BCE. Because of the use of 0 as a digit and the use of the single digit in each position, this system does not lead to any kind of ambiguity when reading or writing numerals. Page number 79. It is for this reason that the Hindu number system is now used throughout the world. The use of 0 as a digit and indeed as a number was a breakthrough that truly changed the world of mathematics and science. In Indian mathematics, indeed, 0 was not just used as a placeholder in the place value system, but was also given the status of a number in its own right, on par with other numbers. The arithmetic properties of the number 0, example, that 0 plus any number is the same number, and that 0 times any number is 0 were explicitly used by Aryabhatta in his Aryabhatiya in 499 CE to compute with and do elaborate scientific computations using Hindu numerals. The use of 0 as a number like any other number on which one can perform the basic arithmetic operations was codified by Brahmagupta in his work Brahma Sputa Siddhanta in 628 CE, as we learnt in an earlier grade. By introducing 0 as a number along with the negative numbers, Brahmagupta created what in modern times is called a ring, that is, a set of numbers that is closed under addition, subtraction and multiplication. That is, any two numbers in the set can be added, subtracted or multiplied to get another number in that set. These new ideas laid the foundations for modern mathematics, and particularly for the areas of algebra and analysis. Hopefully, this gives you a sense of all the ideas that went into writing and computing with numbers in the way that we do today. The discovery of zero and the resulting Indian number system is truly one of the greatest, most creative, and most influential inventions of all time, appearing constantly in our daily lives and forming the basis of much of modern science, technology, computing, accounting, surveying, and more. The next time you are writing numbers, think about the incredible history behind them and all the deep ideas that went into their discovery. Here there is a picture depicting evolution of ideas in number representation. First one, count in groups of a single number. Ukasar, Ukasar, Urapon. Second, group using landmark numbers I, V, X, L, C, M. Third one, choosing powers of a number as landmark numbers. The idea of a base 1, 10 to the power 1, 10 to the power 2, 10 to the power 3, 10 to the power 4, and so on. Fourth, using positions to denote the landmark numbers. The idea of place value system 1729. Fifth one, the idea of 0 as a positional digit and as a number. Rima and her father are looking at this picture. Page number 80. Figure it out. Question number 1. Why do you think the Chinese alternated between the zong and the heng symbols? If only the zong symbols were to be used, how would 41 be represented? Could this numeral be interpreted in any other way if there is no significant space between two successive positions? Question number 2. Form a base 2 place value system using Ukasar and Urapon as the digits. Compare this system with that of the Gumulgals. Question number 3. Where in your daily lives and in which professions do the Hindu numerals and 0 play an important role? How might our lives have been different if our number system and 0 hadn't been invented or conceived of? Question number 4. The ancient Indians likely used base 10 for the Hindu number system because humans have 10 fingers and so we can use our fingers to count. But what if we had only 8 fingers? How would we be writing numbers then? What would the Hindu numerals look like if we were using base 8 instead? Base 5. Try writing the base 10 Hindu numeral 25 as base 8 and base 5 Hindu numerals respectively. Can you write it in base 2? Here we are provided with a map which represents the locations of the different civilizations. They existed in different time periods like Mayan civilization, Egyptian civilization, Mesopotamian civilization, and Chinese civilization. Page number 81. Summary. First point, to represent numbers, we need a standard sequence of objects, names, or written symbols that have a fixed order. This standard sequence is called a number system. Second point, the symbols representing numbers in a written number system are called numerals. Third point, in a number system, landmark numbers are numbers that are easily recognizable and used as reference points for understanding and working with other numbers. They serve as anchors within the number system, helping people to orient themselves and make sense of quantities, particularly larger ones. Fourth point, a number system whose landmark numbers are the powers of a number n is referred to as a base n number system. Fifth point, number systems having a base that make use of the position of a symbol in determining the landmark number that it is associated with are called positional number systems or place value systems. Sixth point, place value representations were used in the Mesopotamian, that is Babylonian, Mayan, Chinese and Indian civilizations. Seventh point, the system of numerals that we use throughout the world today is the Hindu number system, also sometimes called the Indian number system or the Hindu-Arabic number system. It is a place value system with usually 10 digits, including the digit 0, which is treated on par with other digits. Due to its use of 0 as a number, the system enables the writing of all numbers unambiguously using just finitely many symbols and also enables efficient computation. The system originated in India around 2000 years ago and then spread across the world and is considered one of human history's greatest inventions. Chapter 3 ends here.
Ganit Prakash, you were just listening to this audiobook, Textbook of Mathematics for Grade 8. Narration, Swarn Lata Sharma. Sound recordist, Virendra Rawat. Production assistant, Chetna Sharma. Directed and produced by Vimlesh Chaudhary. This audiobook is brought to you by CIET NCERT, New Delhi, India.